Welcome to Lecture 16, Section 3.7. So we are now looking at the average rate of change, or ARC, which is the change of the output values, okay, so our y's, divided by the change of the input values, x. So if you're given two data points, for example, x sub 1, y sub 1, and the other point, x sub 2, y sub 2, you can find the average rate of change between these 2 points by using this formula. And what do I mean by the average rate of change? Well, if I have a line on the x and y coordinate plane, if I had this point and this point, I could figure out how my line changes when I move from this point to the other point. Alright, so for example 1, we are given the table from the U.S. Census Bureau for the population of Texas. Right over there. Where T is the number of years after 2000, and P of T is Texas's population in millions. So if I was to read this set of points right here, T is 0, well, 0 years after 2000 would mean we're still in 2000. So in the year 2000, the population was 20.85 million. Alright. A, find the average rate of change. Okay, so finding the average rate of change, what we're going to do is take one point and another point, so make this point my x sub 1, y sub 1, and this point my x sub 2, y sub 2, and then use our formula here to find the average rate of change. So let's go ahead and do that. I'll rewrite the points and label them better. So I'm going to use the points 0, 20.85, and 1, 21.28. So one thing to note for this problem is we are looking at a linear function for this problem. Should have been noted earlier. We're looking at P of T. So because this is linear, if I chose any one of these two order set pairs, either of the pairs would still give me the same average rate of change because we are looking at a line. So I'm going to go ahead and use these two. Alright, I'll label these my sub 1s, x sub 1, y sub 1, x sub 2, y sub 2. Go ahead and find my average rate of change, which is going to be sub 1s. Now you'll notice, real quick, on this equation, some books will write the sub 1s first and the sub 2s second. Whereas other books will write the sub 2s first and the sub 1s second. So it really depends on the book. Oops, sorry, that's supposed to be a sub 1. As long as the sub 2s are in the front or the sub 1s are in the front. Alright, so plugging this in, we're going to go ahead and I'll use this formula since this is the one I gave you. So putting the sub 1s in first, I have 20.85 minus 21.28. Please notice I use the parentheses because that helps if you have a double negative. And then 0 minus 1. So that's going to equal negative 0.43 divided by negative 1, which is going to end up being positive 0.43. So that is my average rate of change. And the average rate of change is also known as my slope. That's how the line is changing. Alright, so let's find the y-intercept for part B. Well, remember the y-intercept is wherever x equals 0. So we're going to look for where x equals 0. And that point is going to be the one right here. So my y-intercept, remember, always label your y-intercept with the y-intercept notation, and then 20.85. It is a point. So please write it like this. Do not just write your y-intercept as 20.85. That is not acceptable because it is a point. And it's a special point, so we should mark what it is. Alright, so we're going to write an equation for P of T. Well, we have two equations for writing the equations of lines. The slope-intercept form or the point-slope form. Now, the slope-intercept form is the quickest and the easiest one to do, but the hard thing is that it requires a specific point, which is the y-intercept. This one is hard to come by. The nice thing about the point-slope form is this one just needs any old point. It does not matter which point you use. Okay, note both of them require the slope, but the slope-intercept form needs the y-intercept, and the other form just needs any old point. So I'm going to check first to see if I have the y-intercept, because if I do, it'll be simpler to write the equation for this line. If not, I'll go ahead and have to use this form. So do we have the y-intercept? Well, we do. We already found it right there. So because we have the y-intercept, we can go ahead and use the simpler way for writing the equation of a line. We can fill this out. But because we are using the variables t and p of t, I'm going to rewrite my equation in the correct format. So that's going to be p of t, because remember that's the y value. So this is p of t, and then we're replacing x with t. So p of t equals, and my slope is 0.43, and my y-intercept is right there, the 20.85. So slope 0.43t plus 20.85. And there we go, the equation of my line. So now let's go ahead and estimate the population of Texas in 2017. Well, so it wants to know the population in the year 2017, which means we want P of t when, well, 2017. And remember, t is the number of years after 2000. So 2017 is 17 years after 2000. So this is when t equals 17. Alright, so let's use this equation to solve that. So we want p of, and we're inputting 17 for t. That's going to be 0.43 times inputting 17 plus 20.85. Putting that into our calculator, we get that p of 17 equals 28.16, and writing this as a sentence, the population of Texas in 2017 is 28.16, and the unit is million, period. So that was the estimate for the population. Now, part E, when will Texas's population double the population from 2000? So what are we trying to figure out here? Well, we're trying to figure out when the population will be double what it was from 2000. So we want to know when P of t is twice the population from 2000. So what was the population in 2000? The population in 2000 was 20.8. So when P of t is twice 20.8. Well, another way to write that is we want to find out when P of t equals 2 times 20, 0.8. Well, what is 2 times 20.8? That is 41.6. Alright, so we want t, because that's the time we're looking for, t. We want t when P of t is 41.6. So let's go ahead and plug that into our equation. So here's our normal equation. P of t equals 0.43 t plus 20.85. And this time we're trying to find t, and we're substituting in P of t for 41.6. So then I have 41.6 equals 0.43 t plus 20.85. Go ahead and subtract to solve for t. And we get 20, wrong item, 20.75 equals 0.43t. Now let's go ahead and divide by 0.43. Before I do that, I'm going to go ahead and get rid of this so I can do a little better job of writing. Alright. Okay, dividing both sides. And I get 48.25 is approximately t. Well, remember, t is years. So I'm going to actually estimate this probably more to the nearest whole year. That would make more sense. So the nearest year would probably just be 48. So let's go ahead and round that off to about 48. Which means Texas's population will double in 2048. Alright, so now let's take a look. Alright, so when we're using our equations, like the one above, this is just a prediction. It's an estimate, so it's not going to be perfect. So what we're going to look at is this thing called relative error. And the relative error in predictions, okay, this is when we're talking about predicting something based on an equation we're using. The relative error in the prediction is the ratio of the error to the observed value. That is, relative error, you take the observed value, subtract from it the predicted value, divide by the observed value, and you'll get your relative error. Alright, so let's take a look at an example. Use the linear model, P of t equals negative 28t plus 81, which is developed to predict the U.S. population in 2012. Okay, so once again we're using a prediction. A. What assumptions are you making about the rate of change of the population in this prediction? Recall that t is the number of years after 2000. Alright, so it's talking about what's the rate of change. Well, remember, rate of change is the slope. So let's take a look at what the slope is for this problem. And the slope is 2.8. Now, 2.8, let's go ahead and write this as a fraction over 1. So the t value is the population in terms of, I believe, this was millions. And 1 was the number of years. So when I read this slope off, it's saying each year the population grows by 2.8 million. Now the assumption I'm making here is that the growth is constant. Which in real life wouldn't actually be true, because we wouldn't have the same number of people being born every year. Some people are being born, some people are dying. That is not actually a constant known thing. So that's what we're assuming in this simple linear problem. Alright, so what we found out for part B is that the actual U.S. population in 2012 is approximately 314 million. What is the relative error in our prediction? Alright, so what we're going to do first is we need to find out what our prediction is going to be. So first let's predict. And we're going to use our equation, P of t Wait, let me take that back. Let me rewrite this a little better. We want to predict the population. The population in 2030. 2012 using P of t equals 2.8t plus 281. So we're going to go ahead and use this to predict the population. So P of, and we're looking at 2012, so that's 12 years after 2000. So P of 12 equals 2.8 times 12 plus 281, which is going to equal, let's go ahead and type this in, 2.8 times 12 plus 281. It's going to be 314.6. Hey, the prediction is actually pretty close to the actual observed number. So to figure out the error that we had, we're going to go ahead and use the formula above. Okay, which is we're going to take the observed value, which was, oops, wrong one. The observed value was 314 million, and minus from it the predicted value, which we had was 13.4. So let's go ahead. So 314, actually let me back this up a little bit. So the relative error is going to equal the observed value, which is 314, minus what we predicted from our equation, which is 314.6, and divide that by the observed value. So what are we going to get? Well, plugging that into our calculator. So 314 minus 314.6, not too bad. And divide that by 314, and we get approximately negative 0.0019. So that is you could say a pretty small error. Alright, so the relative error is, oops, let me back that up a little better. And that is it for this section.